For the time being, we are just trying to make the problem a bit more realistic, but still simple enough to be so that we will be able to solve it. Now, in principle, we should also add the mass of the string. The string is also massive. So we should also take that into account. Then there is the friction. Well, usually the effect of the friction will be it will just add a net torque to that. A net torque due to friction. But we can add it. Now, if M1 and M2, they are different. Well, you say the effect of the friction. Well, we know that in linear motion, at least, the effect of the friction is to oppose the motion. It will be the same, depending on, well, in that case, if you remember again, in the linear friction case, we first had to study in which direction the system is moving. That is something we have to know. If there is friction, we have to know which direction the system is moving, so that we can determine the direction of the friction force. In this case, in this net torque expression, we should also add the torque created by friction. We should also add it. Well, which direction it will be, it will again depend on whether the system is trying to rotate in this direction or in the other direction. So the sign of this friction, torque created by friction will depend on which way my system is moving. But again, the only modification will be just adding this torque due to friction at this point with some positive or negative sign. All the rest of the calculation will be identical. Another question? So you are all ready for the quiz? Or you have some more questions? See you on Thursday. It will have some angular acceleration. But since its moment of inertia is not zero, and it has a non-zero angular acceleration, the torque acting on it, which should be its moment of inertia times its angular acceleration, this should be non-zero. So the tensions in the string on the left-hand side and on the right-hand side, it should create a net torque acting on my pulley. But since they are acting at equal distances with the same angle from the center, if the tension on the left and the tension on the right are equal, then they wouldn't create any force, any torque acting on my system. So I should have some difference in the tensions on the upper part and on the lower part, on the left and on the right of my pulley, so that that difference will create some torque. Now, to solve this problem, I don't need to assume that M2 is larger than M1 or M1 is larger than M2. I don't need such an assumption. So, as usual with any such problem, you first start with the free body diagrams. You have a pulley. There is these two forces. You can just call them, okay, this is one free body diagram. It is fixed. This is my mass, let's say M1. I have its weight, W1. And then there is the T1, the force due to the tension. I have the second mass, M2. I have its weight, W2, is equal to M2 times G. This is M1 times G. And I also have the T2. Now, if this force, the force acting on M2 due to the tension is pointing upward, the force is T2 force, then the force acting on the pulley would be minus T2. They will be just action-reaction pairs. And the other one on the left-hand side, it will be minus T1. And here I have some force F. Well, that force I will not really care about. So I have three free body diagrams. Then I just write the Newton's equations Okay, since it's one dimensions, everything is almost one dimensional. I just define the T1 force as T1. Let's just call this z-axis, T1 z hat. T2 is T2 in the z hat direction. G is minus G in the z hat direction. And these are all my forces. So for the mass M2, I have T2 minus M2G. This is the net force along the component of the net force along the z direction. This should be equal to M2 times A2. Okay, the accelerations I also define as the acceleration vector of the second mass is A2 in the z hat direction, and the acceleration of the first mass is A1 in the z hat direction. Okay, this is one relation I have. T minus M2G. This is the z component of the force acting on my second mass. This should be M2 times A2. T1 minus M1G. This should be equal to M1 times A2. Now the next thing is the torque acting on my pulley. So let's just take the x-axis to be in this direction. This is your x-axis. This is the y-axis. So the torque created by this tau 1 will be in the positive x-axis. So the net torque acting on my system, tau 1 let's call it, it is in the positive x-axis, and its magnitude will be just T1 times r, because it's acting at a distance r from the rotation axis. It is perpendicular to this radius vector, and the force has a magnitude T1, so T1 times r times sine 90 degrees, which is just 1. Similarly, the torque created by this other cord, the string on the right hand side, so it is just, this is the r vector, the application point, the force is downward, so my thumb points the direction of the torque, which is inside the blackboard, so it's in the minus x direction. So tau 2 will be T2r in the minus x direction. This is the tau 2 vector. So this just tells me that the net torque acting on my system, if I write it at tau in the x-hat direction, tau is equal to T1 minus T2 times r. So this is the net torque acting on the pulley. Now the analogous equation to this one for rotations is just T1 minus T2 times r is the moment of inertia of my object, of the pulley, times its angular acceleration, where the angular acceleration vector I again write at alpha in the x-hat direction. So what are my unknowns? I don't know alpha. I don't know T1. I don't know T2. I don't know A1. And I don't know A2. Okay, these are my unknowns. I have 5 of them. Now, currently I only have 3 equations for my 5 unknowns. I need 2 more. Well, one is just since mass 1 and mass 2, they are attached to the same string, if one of them goes up, the other one should go down. So their displacements should have opposite signs. That means their velocities should always have opposite signs, which means that their acceleration should always have opposite signs. One of them has acceleration A1, the other one has acceleration A2. So A1 should be equal to minus A2. So this is the 4th equation we have. Now, the acceleration of, okay, so this is my pulley. Here I have my masses. Now, M1 and M2. If M1 is accelerating upwards, then this point is accelerating in this direction, this point has accelerating in this direction. They all have tangential accelerations. And the tangential acceleration, if A1 is, let's say, positive, if A1 is positive, then this is going up. So it means this point has a, okay, so let me just, alpha is in this direction. Alpha cross R, let me just take this point. This is my R vector. This is the alpha vector pointing out of the blackboard. Alpha, R, or R cross alpha, let's say, is in this direction. This is my alpha cross R vector. R cross alpha vector, sorry. Now, this is, of course, assuming alpha is in this direction. If alpha is in this direction, this is the R cross alpha. But if alpha is in this direction, it just means that it is accelerating like this. So this is equal to, if we just take this point, not that point, but this, if you consider this point, alpha cross R is in this direction, R cross alpha is in that direction. So that is the tangent, sorry. So this is minus A tangential. A tangential is alpha cross R. Now, why is this so? Remember, we had the velocity of a point on our rotating object is omega cross R. So if velocity is omega cross R, the tangential acceleration is just alpha cross R. They're due to the change in W. Now the tangential acceleration. Okay, we said that alpha is this. For that point, where should I erase? So this is my Pulley. I'm looking at this point. I know that this point has acceleration A1 because it is connected to this string over here. It has the same acceleration. But this is the tangential acceleration of that point. And the tangential acceleration of a point is alpha cross R. Now, alpha is alpha x hat. R, okay, this is x, y, and z. Cross R in the minus y hat direction. Minus r y hat. Because I'm looking at this point at a distance r from the origin. So it is in the minus y direction. Minus r alpha, well, x cross y, x cross product y gives me a vector in the z direction. So the tangential acceleration is minus r times alpha, but this is equal to a1. So a1 should be equal to minus r times alpha. And this is my fifth equation. So remember, I had these two equations for the point masses. I had this third equation, third dynamics equation for the massive Pulley. That gave me three equations. Then I had this relation because mass 1 and mass 2 are attached to the same point, to the same string. And then I have this equation because the string is not slipping over the pulley. That is our assumption. So this point moves with the same velocity as this point, same speed as this point. So these 2 points have the same speed and hence the same accelerations. So that is what I use. This is tangential acceleration is A1. And this is my fifth equation for 5 unknowns, which you can solve. Now, any questions on how to write down these equations? Well, the most important thing is to just be able to write down these equations. Then, of course, you can do some algebraic mistakes, but they are not as important. So any questions on how to write down these equations? Come on, you should be at least asking me how did we obtain that equation? Yes? Okay, I will repeat that. But these 4 equations, any questions on these 4 equations? This is just for point masses, Newton's dynamics for point masses. This is just the torque for the dynamics for rotating objects. Well, these 3 is in fact what we had done previously. There is nothing new in these 3. This one is new. We should be creating some torque on the pulley. And this one is new. Now I will just repeat how we obtain this. A1 is equal to minus R alpha. Well, remember, okay, this is how we chose the coordinate axis. So at this point, I have a downward force with magnitude T1. So the torque is R cross F. So this is the direction of the torque. This is my position vector relative to my rotation axis, or my reference point, and this is the force. So R cross F is in this direction. So the torque created by the first the tension on the left-hand side is T1 times R times X. It's in the positive X direction. Now the other force, here I have another force, minus T2. And okay, this is my reference point. This is the position of the point where this force acts. The force is acting at this point. This is my T2. This is my R2 cross T. So the torque created by this force is inside the blackboard. But inside the blackboard is the minus X direction. This X axis is like this. So tau 2 is T2 times R. It's in the minus X direction. So the sum is just T1 minus T2 times R in the X direction. I don't know whether T1 or T2 is positive. It might be that T1 is larger than T2. In that case, the torque is in the positive X direction. Or it might be that T2 is larger than T1. In that case, the torque will be in the negative X direction. But I mean, this equation contains both of the cases. This is valid in both cases. Now, let's come to this one. I mean, it's kind of easy to remember this one. It's just like the speed of any point is nothing but the angular velocity times the distance from the axis of rotation, and the acceleration of any point, the tangential acceleration, is nothing but the angular acceleration times r. Well, this distance is fixed, so if you just take the time derivative of this relation, you get the tangential acceleration, and the time derivative of this one is just alpha. Now, the difficulty is the signs. These are for the magnitudes. So is it a plus or minus? So for that one, the best thing is to use the vector notation, because vectorially, we know that V is equal to omega cross R. Okay, if you want to use the right-hand rule, by the way, another thing that you should pay attention to is that x cross y should give you the z unit vector. So this is my x, this is my y. X cross y gives me the z axis. So these three axes have the correct orientation. Now this is how you should define your coordinate axes to be consistent. Now v is omega cross r. So the tangential acceleration is alpha cross r. This is my tangential acceleration. Now, how do I know that the velocity is omega cross r? Well, the magnitude of the velocity is always omega cross r, omega times r. Now, if you just assume that this is rotating in this direction, so omega is such a vector. If you look at this point, the velocity of that point would be downward. And if it's rotating like this, omega is pointing upwards, omega cross r points downwards. So omega cross r has the same magnitude as your velocity vector, and it has the same direction as your velocity vector, so the velocity vector can always be written as omega cross r. Then from this one, just taking again the derivative, you can obtain this one. This is valid only for the tangential acceleration though. Or you can think of it like this. In the previous example, we assume that it is rotating like this, and it is accelerating in this direction. So it has an acceleration vector pointing in this direction, angular acceleration vector. Its linear acceleration is pointing downward because it is going faster and faster. So alpha pointing in this direction, cross r points downwards. So this alpha cross r vector has the same magnitude as your tangential acceleration and also the same direction as your tangential acceleration. So those equations are valid. Now let's look at this point. This point moves together with my mass m1. If my mass m1 is going down by 1 meters per second, this point should be going down by 1 meters per second. If my mass m1 is accelerating downwards by 1 meters per second squared, this point over here should also be accelerating downwards by 1 meters per second squared, because they are at the end of the same string. So this should be equal to a1. The rest is just putting it in the vectors. So I know I had defined my alpha vector like this. It is in the x direction, plus or minus x direction, depending on the sign of this alpha. R vector, well, R vector is this vector. This is nothing but R in the minus y hat direction. So if you just put everything back, so you get this is equal to alpha vector is alpha in the x hat direction. R vector is minus r y hat direction. So this is minus alpha times r x cross y minus alpha r z hat. This is the a1 vector. A1, did I erase it? No, I did erase it. The A1 vector, I defined as A1 along the z hat direction. So this already tells me that this A1 over here is, with that minus sign, minus alpha r. Well, you can also guess it by just assuming that alpha is positive, r is positive, assuming alpha is positive, just for a particular case. We know that A1 should be alpha r, but if you cannot define the sign, just assume that alpha is positive. So alpha is positive. So it is, initially if it is rotating like this, it is starting to rotate faster and faster. So this point should have a downward acceleration if alpha is positive. But A1 is pointing up. If alpha is positive, since that point is accelerating downward, A1 should be negative. It is accelerating downwards. Alpha r is positive if alpha is positive, so you should put this minus sign to make sure that A1 is negative if alpha is positive. But this also holds for if alpha is negative, because if alpha is negative, then A1 should be positive, and negative makes positive. This is valid whether alpha is positive or negative. Okay, the solution of these 5 equations, I will not go over them. So these are what we have. Well, as usual, whenever you have many equations, and you solve many equations in many steps, it's quite likely that you will have some mistakes, some sign mistakes somewhere. So it's a good idea to compare certain limiting cases. For example, what happens if M1 is equal to M2? What you expect if M1 is equal to M2? Well, the system should move at constant velocities. Constant angular velocity, constant linear velocities. That's what you expect. If the system is initially at rest, the system should always remain at rest. And in that case, if M1 and M2, they are equal, well, the linear acceleration we find to be 0. The angular acceleration, we find it to be 0. So that is what we would expect. Another limit, you can say that, okay, if M2 is very large, much larger than M1, then the masses here will not have any effect. You don't expect the mass of the Pulley or the mass 1 to have significant effect. So the acceleration should be g. M1 should be going downward with an acceleration g, and M1 should be going upward with an acceleration g. That's what we would expect if M2 is very large. That is, if M2 is very large compared to other masses, then A1 should be g, is upward, and A2 should be minus g. Well, let's see. If M2 is very large compared to all the other masses, well, M1 you can just ignore. The moment of inertia of the Pulley you can just ignore. So you have the M2r squared divided by M2r squared g. So this number just becomes very close to g if M2 is very large. It means A1 is equal to g and A2 is equal to minus g, as we had expected. If you look at alpha, if M2 is very large, you see that it is, well, this just goes away. M1 you can ignore, I you can ignore. Alpha just becomes minus g over r. Did you expect that? With the minus sign. G over r kind of you would expect, because all the points on the rim should have the same tangential acceleration as this mass M2. And they should all have an acceleration g, linear acceleration g. So the angular acceleration should be just g over r. That is what we expect. What does that minus sign tell us? It just tells us that alpha is in this direction. It's not in this direction, it's in this direction. It just means that they are accelerating like this. That minus sign just tells us that all the points at the rim, they just accelerate in this direction. And that is what we expected, because this is infinitely heavy. It accelerates with an acceleration g pointing downward. Well, let's look at the tensions. What do you expect about the tensions? Should be the same. Let's say if the magnitudes are the same in the limit that M2 is very large. Now, if M2 is very large, so here we say that you can just ignore this M1, ignore this. So we have M2s, they just cancel. Let me write it down. It looks like a long expression. Now we are looking at, start with T1. If M2 is very large, T1 becomes m1g times 2 m2 r squared divided by m2 r squared. So I just ignore this term and this term compared to the m2. It is very large. I ignore the moment of inertia compared to m2. So this is what remains. If I do the cancellations, T1 is 2 m1g. This is my T1. Let's look at T2. Again, I will ignore this m1 and m2. Well, I cannot really do anything because I don't know whether it is much larger or smaller than m1. So I have m2g I plus twice m1 r squared divided by m2 r squared. These m2s, they cancel. So T2 is g times I plus 2 m1 r squared divided by r squared. Or I can also write this as g over r times r squared I over r. Now g over r, I over r, plus twice m1g. So they are definitely not equal. Does it make sense? So okay, so we had some expectation. Your friend had an expectation that in the limit that m2 is very large, the tensions had to be equal. That is what she expected. But it turned out that they are not equal. So the possibilities are either we did something wrong in the calculation, or our expectation was wrong. So if our expectation was wrong, that signals to us that there's something we are not really understanding. So what might be wrong in our expectation? The string is strong enough. It doesn't break. Abate? So let's look at T1. Well, your friend almost had a point though. If you look at this, okay, let me just write it again more clearly. T2. T2 turned out to be T1 plus GI over R squared. If I didn't do any mistake, yes. So if the moment of inertia of the Pulley was 0, then T1 would have been equal to T2. But even if we have M2 infinitely large, we still need some imbalance between T1 and T2 to create a torque to start the Pulley rotating. So we do have this difference between T2 and T1. T2 is larger than T1. That is what we expected though. The tension here should be larger than this one because this tension should create a larger torque than this one. So how could we have expected that T1 should be equal to twice M1G? That we could have guessed. So what is the acceleration of M1 in the limit that M2 is very large? It's G. Which direction? G pointing upwards. That's our positive Z direction. So what should be the net force acting on it relative to its weight? The net force acting on it should be equal to its weight, but it should be pointing upwards because it's accelerating with gravitational acceleration in the upward direction. So it has its weight downwards, so the tension should be such that the net force should equal to its weight in magnitude, but pointing in the opposite direction. So the force due to the tension should be twice its weight. And this is what we obtained. T1 is twice its weight. Its magnitude is twice its weight. We know that its direction is pointing upwards. So if you add the weight of the object to the force created by this tension, so it is just a vector pointing upward, which is equal to its weight. And that is what we would expect. What about this GI over R? Do you expect this GI over R? Yes. Well, the thing is over here. T1 minus T2 times R is the net torque. So if T2 is given by this expression, then T1 minus T2 is T1 minus T2 times R. Let me write it down. T1 minus T2 times R. This is the net torque created by the tensions. This is equal to G over R times I. The moment of inertia, the torque, with a minus sign. Torque, the net torque created by the tensions, is equal to the moment of inertia times the angular acceleration. G over R is the angular acceleration. We had said that the alpha should be G over R. G over R in the limit that M2 is infinitely large. So even this one we could have guessed with a little bit of thinking. It wouldn't be that obvious, this one. T1 would have been obvious what should be. And the accelerations are accelerations A1, A2, and alpha in the limit that M2 goes to infinity is kind of obvious. Any questions on this problem? Any other limit that you think would be interesting? Well, depends on the directions that we choose. Remember, if you so where's my free body diagrams? Okay, so well, the torque created by T1 is T1 times R in this direction. And that is the direction I chose as the positive X direction. And T2 is acting relative to the axis of rotation in this direction. This is the action point. It points downward. So this is the direction of the torque created by T2. It's in the minus X direction. Depends on the coordinate axis I choose. So but you should always pay attention to the fact that you choose a coordinate axis at the beginning of the problem and use the same coordinate axis throughout the problem. You don't flip your coordinate axis in between. In the beginning of the problem, I chose my coordinate axis such that X points in this direction, Y points in this direction, and Z points in that direction. So in this coordinate axis, the torque created by this T1 is in the positive X direction. The torque created by this force over here is in the minus X direction. That is according to the axis I choose. Any questions? By the way, let me just remind you one fact. The time left is not enough for another example, but it's enough for a quiz. So anybody that has a question? Now the angular vector, no, not necessarily. You see, if you imagine this pulley, now at a given instant, this pulley can be rotating like this, in which case it will have angular velocity in this direction, or it can rotate like this, in which case it can have some angular velocity in that direction. But the torque created by this T1 is always in this direction. The torque created by this T2 is always in the opposite direction. independent of what is the angular velocity of this pulley. That is the definition. The torque is equal to I times alpha. Torque is always equal to I times alpha. And I define my alpha to be alpha in the x-hat direction. My torque is T1 minus T2 times R in the x-hat direction. I don't know the sign of alpha. The sign of alpha should be given at the end of the calculation, depending on my masses. Alpha might be positive or negative. But whether alpha is positive or negative, this relation always holds. So I don't need to assume that alpha is positive. Well, it is in the x direction, but depending on the sign of alpha, it is either in the positive x direction or in the negative x direction. And if you look at our results, well, you see, if M2 was larger, that is the case we assume, then alpha was negative. So the angular acceleration points inside the blackboard. If M1 was larger, the angular alpha would be positive. It just tells me that the angular acceleration vector is pointing out of the blackboard. No more questions? You are all prepared. Oh, yes, there is one. Well, that is, if you look at this one, I'm just taking the limit as M2 is very large. So I can just ignore this M1 and ignore this I. Because M2 is very, very large. So M2 R squared is much, much larger than I. So I can just ignore this I. I'm just assuming I have a small pulley here and a very large mass attached to it. That's the assumption. Yes? Well, why do we ignore the friction? For the time being, we are just trying to make the problem a bit more realistic, but still simple enough to be so that we will be able to solve it. Now, in principle, we should also add the mass of the string. The string is also massive. So we should also take that into account. Then there is the friction. Well, usually the effect of the friction will be it will just add a net torque to that. A net torque due to friction. But we can add it. Now, if M1 and M2, they are different. Well, you say the effect of the friction. Well, we know that in linear motion at least, the effect of the friction is to oppose the motion. It will be the same depending on, well, in that case, if you remember again, in the linear friction case, we first had to study in which direction the system is moving. That is something we have to know. If there is friction, we have to know which direction the system is moving so that we can determine the direction of the friction force. In this case, in this net torque expression, we should also add the torque created by friction. We should also add it. Well, which direction it will be, it will again depend on whether the system is trying to rotate in this direction or in the other direction. So the sign of this friction, torque created by friction will depend on which way my system is moving. But again, the only modification will be just adding this torque due to friction at this point with some positive or negative sign. All the rest of the calculation will be identical. Another question? So you are all ready for the quiz? Or you have some more questions? See you on Thursday.